Ancient temples hold a mystery that has baffled archaeologists for millennia. Perfectly clean walls without a single smudge of soot, mysterious niches, and strange reflective surfaces. How did our ancestors illuminate sacred spaces without leaving traces of fire? Today, we will reveal the secrets of forgotten lighting technologies, from the solar mirrors of the Egyptian pyramids to Nikola Tesla's wireless lamps. A journey into the world of light, where ancient wisdom meets modern science. Subscribe to our channel to learn more amazing facts about the forgotten technologies of our ancestors. Now, let's discuss in the comments. Do you think that some ancient technologies could have been so advanced that they surpass the capabilities of their time? Perhaps our ancestors knew secrets that we are only now beginning to understand. Imagine an ancient temple where sacred rituals were performed thousands of years ago. The walls are covered with the finest frescoes, the ceilings are decorated with intricate patterns, and the stone blocks are fitted together with jeweler's precision. And yet, there are no traces of soot from torches or oil lamps. It is as if this magnificent interior was illuminated by invisible light. This mystery has puzzled archaeologists and historians for decades. In the temples of ancient Egypt, in the underground sanctuaries of Rome, in the Byzantine basilicas, everywhere the same picture, perfectly preserved paintings on which not a single spot should have remained if open sources of fire had really burned here. Early researchers suggested that the ancients used some kind of special, smokeless torches. Others hypothesized that the walls were regularly cleaned by armies of servants. Still others suggested the use of some kind of mystical light sources bordering on magic. But the truth, as is often the case, turned out to be both simpler and more complex than all the assumptions. Our ancestors did indeed possess amazing lighting technologies that we have almost forgotten. Technologies based not on mysticism, but on a deep understanding of the physics of light, optics, and the chemistry of combustion. The mystery began to unravel with a careful study of the architectural features of ancient structures. Archaeologists began to notice strange niches in the walls, unusual holes in the ceilings, and mysterious polished surfaces located at specific angles. What were previously considered decorative elements or accidental damage turned out to be parts of sophisticated lighting systems. In Egyptian temples, entire networks of polished bronze mirrors were discovered, directing sunlight into the farthest corners of underground rooms. In Roman villas, they found the remains of a system of lenses that concentrated the light of oil lamps and increased their brightness tenfold. In Byzantine churches, they discovered ingenious designs that allowed a single light source to illuminate huge spaces without producing soot. Each new discovery lifted the veil of mystery over the forgotten knowledge of our ancestors. It became clear that the history of lighting is not just an evolution from bonfires to electric light bulbs. It is a series of ingenious inventions, many of which were lost over the centuries and are only now beginning to be revived thanks to modern technology. A journey into the world of forgotten lighting technologies is a journey to the origins of human ingenuity, to a time when every ray of light was worth its weight in gold, and the ability to control it was valued as highly as the art of magic. 30,000 years ago, when our distant ancestors were just beginning to master fire, they were already thinking about a problem that still concerns engineers today: how to get maximum light with minimum smoke. In the Lascaux caves in France, archaeologists discovered the first indoor lighting system in human history. Imagine Cro-Magnons, armed only with stone tools, created a complex ventilation system. They pierced 2 holes in the rock that connected at the top. Smoke from the fire rose through one hole, while rainwater flowed through the other into a specially hollowed-out pit. This design allowed them to keep a fire burning deep underground without suffocating from the smoke. But the real breakthrough came with the invention of reflective surfaces. 15,000 years ago, cave dwellers began polishing the walls of their corridors, turning them into primitive mirrors. The light from oil lamps made of hollowed-out stones and animal fat was reflected off the polished surfaces and penetrated into the farthest corners of the underground dwellings. These ancient lighting technicians understood principles that modern science only formulated in the 17th century. They knew that the angle of incidence is equal to the angle of reflection, and used this knowledge to create complex lighting systems. In some caves, entire chains of reflective surfaces have been found that transmitted light over distances of up to 100 meters. At the same time, the light sources themselves were also developing. While the first lamps were simple stone bowls with wicks made of moss or grass floating in fat, over time the design became more complex. Lamps with multiple wicks appeared, increasing the brightness. Devices were invented to regulate the height of the flame, and special reservoirs were created to ensure a uniform supply of fuel. The invention of portable light sources deserves special attention. 5,000 years ago, the Japanese learned to catch fireflies and keep them in special cages made of thin wooden slats. Such a living lantern burned all night without requiring fuel, while providing a surprisingly even, non-flickering light. British tribes of the same era found another solution. They used fatty fish as torches. Special types of fish, rich in oils, were skewered on sticks and set on fire. Such a torch burned for several hours, and when the fuel ran out, it turned into nutritious food for travelers. Mediterranean peoples discovered the amazing properties of olive oil. It turned out that properly purified olive oil burns with virtually no smoke or soot, while providing a bright, even light. This discovery became the basis for the creation of the first clean light sources that could be used indoors without the risk of suffocation or staining the walls. The crowning achievement of ancient lighting engineers was the creation of combined systems. They learned to combine several light sources with reflective surfaces to create complex lighting installations. Some of these systems are still in use today. For example, Buddhist monasteries in Tibet still use oil lamps, whose light is amplified by a system of polished copper reflectors. 5,000 years ago, a real revolution in lighting technology took place in the Nile and Euphrates valleys. The ancient Egyptians and Mesopotamians transformed the primitive oil lamp into a sophisticated engineering tool capable of competing in efficiency with modern light sources. The key breakthrough was the understanding of the relationship between the shape of the lamp and the quality of lighting. Egyptian craftsmen discovered that the configuration of the reservoir affected not only the brightness of the flame, but also the uniformity of combustion, fuel consumption, and the amount of soot produced. They began experimenting with different shapes, from simple round bowls to complex multi-level designs. The lamp with an adjustable wick became a true masterpiece. Egyptian engineers created a mechanism that allowed the wick to be raised or lowered without extinguishing the flame. This made it possible to precisely control the brightness of the light and the consumption of oil. Such lamps could burn continuously for several days, requiring only periodic refueling. The invention of multi-wick lamps was also revolutionary. Instead of one large flame, the Egyptians learned to create several small ones located around the perimeter of a special reservoir. This design provided more uniform lighting and allowed the brightness to be adjusted by lighting or extinguishing individual wicks as needed. Meanwhile, in Mesopotamia, the chemical composition of fuel was being improved. Babylonian alchemists discovered that adding certain plant extracts to oil could significantly improve the quality of combustion. Some additives made the flame brighter, others reduced the amount of smoke, and still others prolonged the burning time. There were even compounds that gave the flame different colors, from golden to greenish. The invention of wicks made from specially treated papyrus deserves special attention. Egyptian craftsmen learned to weave wicks in such a way that they self-cleaned during combustion, removing the products of incomplete combustion and maintaining a stable flame shape. The secret lay in a special method of preparing papyrus fibers and impregnating them with a mixture of salts that prevented the formation of soot. Archaeological finds testify to the existence of entire workshops in ancient Egypt that specialized in the production of oil lamps. Each workshop had its own signature style, a special shape of the reservoir, a characteristic pattern, or a special manufacturing technology. The highest quality lamps were decorated with intricate reliefs and inlays, turning them into true works of art. But the most amazing achievement was the creation of automatic lamps with a self-sustaining oil supply. Egyptian engineers invented a system of communicating vessels that ensured a constant fuel level in the burner. Such lamps could operate without human intervention for several weeks, which was especially important for lighting temples and tombs. The impact of these inventions on the development of civilization cannot be overestimated. Reliable artificial lighting made it possible to extend the working day, develop night crafts, and hold evening ceremonies and rituals. It was thanks to these sophisticated oil lamps that the great libraries of Alexandria and Pergamum were created, where scholars could work with texts at any time of the day or night. The secret of the clean walls of Egyptian temples lies not in magic, but in an ingenious engineering system that turned sunlight into a powerful tool for interior lighting. Egyptian architects created the first light guide system in human history, using principles that modern science only rediscovered in the 20th century. The system was based on specially placed openings in the temple roof, which at first glance looked like ordinary windows. However, a detailed study showed that each opening had a precisely calculated diameter and was positioned at a specific angle to the horizon. Egyptian engineers took into account the movement of the sun across the sky during the day and seasonal changes in its trajectory. But the most surprising element of the system was the polished bronze mirrors built into the walls of the temples. These mirrors were not arranged randomly, but formed a complex network of reflective surfaces. A ray of sunlight entering through an opening in the roof would hit the first mirror, reflect off the second, then the third, and so on, until it reached the farthest corners of the temple. The accuracy of the calculations amazes modern engineers. Egyptian craftsmen took into account not only the geometry of reflections, but also the loss of light on each mirror, the gradual contamination of reflective surfaces, and even seasonal fluctuations in the transparency of the atmosphere. The system worked so effectively that at noon, the temple was almost as bright as outside. For cloudy days and evening rituals, the Egyptians developed a hybrid system that combined reflected sunlight with artificial lighting. Oil lamps were installed in special niches, equipped with their own polished metal reflectors. The light from the lamps was amplified and directed by the same system of mirrors that worked with the sun's rays during the day. Temple servants played a special role. and they can be called the first lighting technicians in history. They kept the mirrors clean, adjusted their position depending on the season, and monitored the operation of the oil lamps. There was even a special position called Keeper of the Light, whose duty was to maintain perfect lighting in the temple. In some temples, the remains of even more complex systems have been found. For example, in the Temple of Dendera, traces of movable mirrors have been found that could turn to follow the sun, like modern heliostats. These mirrors were controlled by a system of counterweights and ropes, an ancient version of an automatic drive. No less intriguing is the colored lighting system found in the tombs of the pharaohs. Egyptian craftsmen learned to pass sunlight through translucent plates made of various minerals, obtaining red, blue, green, and yellow light. By combining colored rays with mirrors, they created a mystical atmosphere in the burial chambers, which was supposed to symbolize the transition to the afterlife. Archaeological research shows that Egyptian temples were not just religious buildings, but also unique research centers for the study of light. Priests conducted experiments with various reflective materials, tested new mirror configurations, and studied the behavior of light in different conditions. The results of these studies were recorded on papyrus, many of which have survived to this day. The influence of Egyptian lighting technology spread far beyond the Nile Valley. Elements of Egyptian systems can be found in Greek temples, Roman basilicas, and even in medieval cathedrals in Europe. When the Roman legions conquered Egypt, they not only took the treasures of the pharaohs to Rome, but also adopted their lighting technology. However, Roman engineers did not stop at simple copying. They improved on Egyptian inventions and created lighting systems that surpassed anything known in the ancient world. The greatest achievement of Roman lighting technology was multi-stage lamps capable of illuminating huge spaces with a single light source. The principle of operation was based on cascading light amplification. Each subsequent element of the system increased the brightness received from the previous one. At the center of the system was a powerful oil lamp of a special design, surrounded by a parabolic reflector made of polished bronze. This reflector collected all the rays of light into a parallel beam, which was directed onto a system of rock crystal lenses. Roman craftsmen learned to grind lenses with such precision that they could focus the light into a spot only a few centimeters in diameter. The focused beam of light fell on the central mirror of the system, a huge disc of polished silver mounted on a rotating mechanism. From this mirror, the light was reflected onto dozens of small mirrors located throughout the room. Each small mirror was adjusted to direct the light to a specific area, a statue, a fresco, or an altar. Operating such a system required a high level of skill. In Roman villas and public buildings, there was a special position called luminarius, or lighting master. He was responsible for adjusting the mirrors, filling the lamps, and regulating the brightness depending on the time of day and the nature of the events taking place. Roman baths deserve special attention, as lighting technology reached unprecedented perfection there. Underwater lights were used in bath complexes, sealed lamps installed at the bottom of pools behind thick glass panels. The lights flickering under the water created a fantastic atmosphere, turning bathing into an almost mystical ritual. Roman engineers also improved the color lighting system. They learned how to make colored glass of various shades and create complex lighting compositions. In some villas, the remains of systems have been found that allowed the color of the lighting to be changed throughout the evening, from golden to red, then to blue and green. The crowning achievement of Roman lighting engineering was the light clock, a device that showed the time using moving beams of light. Sunlight reflected by a system of mirrors was projected onto a special scale marked on the wall. As the sun moved across the sky, the spot of light moved along the scale, showing the current time with an accuracy of a quarter of an hour. No less impressive were the Roman lighthouses, equipped with powerful lighting systems. The Lighthouse of Alexandria, one of the 7 wonders of the world, used a combination of huge mirrors and lenses to create a beam of light visible from a distance of more than 50 kilometers. The system worked on the principle of a modern searchlight, collecting light from a fire into a narrow, directed beam. Roman military engineers also used lighting technology for military purposes. They created portable mirror systems capable of blinding enemy soldiers or setting fire to siege engines. There is documentary evidence of the use of such light cannons in the defense of Syracuse and other fortresses. The Roman legacy in the field of lighting technology proved so significant that many principles of Roman lighting technology are still in use today, from car headlights to theater spotlights. With the fall of the Western Roman Empire, many technological achievements of antiquity were lost. But in Byzantium, lighting traditions were not only preserved, but also developed further. Byzantine craftsmen, inspired by Christian symbolism of light as a divine principle, created lighting systems of unprecedented beauty and complexity. A key innovation was the use of polished bronze made from a new alloy, which Byzantine metallurgists kept a closely guarded secret. This alloy had amazing reflective properties. Mirrors made from it did not tarnish for decades and provided a nearly perfect reflection. The secret of the alloy was lost after the fall of Constantinople and has not yet been solved by modern scientists. A revolutionary invention was the light wells, vertical shafts piercing the building from top to bottom and equipped with a system of mirrors. Sunlight entering the upper part of the shaft was reflected from mirror to mirror, descending to the lowest floors of the building. This system allowed underground rooms to be lit with natural light even in cloudy weather. Hagia Sophia in Constantinople had the most complex lighting system in the medieval world. 40 windows in the dome functioned not only as sources of light, but also as elements of a giant optical system. Each window was equipped with a system of mirrors and lenses that directed light to specific points in the interior. Mosaics played a special role in Byzantine lighting technology. Byzantine craftsmen learned to use gold and silver tesserae, mosaic pieces, as miniature mirrors. A correctly positioned mosaic could collect scattered light and direct it in a concentrated beam to the desired point. This made it possible to create the effect of glowing saints. Their faces literally shone in the dim light of the temple. Byzantine engineers also improved oil lamps by creating the first automatic fuel supply systems in history. Special reservoirs installed under the dome of the temple were connected to the lamps by a system of tubes. Oil flowed to the burners under the force of gravity, and special valves regulated the flow rate. Portable lighting systems were no less impressive. Byzantine craftsmen created folding reflectors made of polished metal that could be quickly assembled in the field. Such systems were used by the military during night operations and by merchants on caravan journeys. Lighting effects for religious ceremonies constitute a special page in the history of Byzantine lighting technology. During important holidays, all lighting systems in temples were turned on simultaneously, creating fantastic illuminations. Witnesses describe these spectacles as heaven descending to earth. So impressive were the light shows. Byzantine craftsmen also experimented with dynamic lighting effects. They created rotating mirror systems driven by jets of hot air from lamps. The reflected rays danced across the walls of the temple, creating the illusion of moving light. The secrets of Byzantine lighting technology were carefully guarded and passed down from master to apprentice. There were entire dynasties of lighting masters, each with their own family secrets and special techniques. Unfortunately, most of this knowledge was lost along with the Byzantine Empire. The influence of Byzantine lighting technologies spread far beyond the empire. Elements of Byzantine systems can be found in Russian churches, Italian cathedrals, and even in the mosques of the Ottoman Empire. The Byzantine heritage became a bridge connecting ancient lighting traditions with the achievements of the Renaissance. Medieval monasteries became true centers for the preservation and development of lighting technologies. Monks, who spent long hours copying manuscripts and studying sacred texts, were in dire need of high-quality lighting. It was within the walls of monasteries that the first lens and reflector systems designed specifically for reading and writing were created. The invention of reading lenses, magnifying glasses mounted on special stands above writing desks, was revolutionary. Monk glassmakers learned to make lenses of varying curvatures, each of which provided a specific magnification. By combining several lenses, it was possible to create a powerful optical system that turned the dim light of a candle into a bright, focused beam. The monastery scriptoria, rooms for copying books, deserve special attention. It was here that the first work lighting system in history was created, taking into account the characteristics of human vision. The monks discovered that for comfortable reading, the light must fall at a certain angle without creating shadows from the hand and without dazzling the eyes. To solve this problem, swivel reflectors were invented, a system of mirrors that could be adjusted individually for each workstation. The central light source, a powerful oil lamp, was installed in the center of the scriptorium, and the reflector system distributed its light among all workstations. The monks also improved the design of the light sources themselves. They created special candles from beeswax with the addition of aromatic resins, which burned evenly and did not smoke. The wicks for these candles were made from specially treated flax, which did not require constant trimming. Some monasteries used illuminated water clocks, devices that showed the time even in complete darkness. The principle of operation was based on the gradual illumination of different sections of the water reservoir as the water level changed. Such clocks allowed the monks to accurately observe the schedule of night prayers. Folding travel lamps for itinerant monks were a revolutionary invention. These devices consisted of telescopic tubes, mirrors, and lenses that could be quickly assembled into a compact lighting system. When folded, such a lamp could be placed in a small case, and when in working order, it provided enough light for reading or writing. Monastic craftsmen also experimented with a new type of sundial, a device that could show the time not only during the day, but also at night. For this purpose, they used the moon and stars, as well as a system of mirrors that directed the moonlight onto a special scale. The accuracy of such clocks was not high, but it was quite sufficient for monastic life. Colored stained glass played a special role in monastic lighting technology. Monks learned to use stained glass not only as decorative elements, but also as part of the lighting system. Colored light passing through the stained glass was directed by a system of mirrors to various parts of the temple, creating a mystical atmosphere during services. The first systems for protecting books from the harmful effects of light were created in monastery libraries. Monks discovered that direct sunlight could damage parchment and ink, and developed a system of diffused lighting in which books received enough light for reading but were not exposed to the destructive effects of ultraviolet rays. The knowledge accumulated in medieval monasteries became the basis for the development of optics in the Renaissance. Many principles of monastic lighting technology were later used in the creation of the first telescopes and microscopes. While Europe was experiencing the Dark Ages, the Arab world was experiencing a real boom in science and technology, including revolutionary advances in lighting. Arab scientists did not simply preserve ancient knowledge, they significantly developed it, creating the theoretical basis for modern optics and combustion chemistry. The greatest contribution of Arab alchemists was the systematic study of combustion processes. They were the first to understand that the quality of light depends not only on the design of the lamp, but also on the chemical composition of the fuel. Jabir ibn Hayyan, the father of Arab alchemy, created the first classification of combustible substances and described methods for purifying them to obtain a smokeless flame. Arab craftsmen invented oil distillation, obtaining various fractions with different combustion properties. Light fractions produced a bright but quickly burning flame, while heavy fractions burned longer but less brightly. By mixing different fractions in certain proportions, it was possible to obtain fuel with predetermined characteristics. The use of wicks made of asbestos, a mineral that does not burn in fire, was a revolutionary discovery. Such wicks lasted indefinitely and did not need to be replaced. Arab merchants brought asbestos from distant deposits in Cyprus and Afghanistan, turning it into one of the most valuable commodities of the time. Arab opticians, having studied the works of Ptolemy and other ancient authors, created the first theory of lenses and mirrors. Al-Hazan, a great Arab scientist of the 11th century, wrote the Book of Optics, in which he was the first to mathematically describe the laws of refraction and reflection of light. His work became the basis for the creation of more sophisticated lighting systems. Arab lighthouses, which surpassed even the famous Lighthouse of Alexandria in power, became a practical application of theoretical knowledge. Light towers equipped with systems of parabolic mirrors made of polished steel were built in Córdoba and Seville. These mirrors were so large that their manufacture required the work of entire workshops for many months. Arab astronomers created the first optical instruments for observing celestial bodies. They invented the illuminated astrolabe, a device that allowed astronomical measurements to be made even at dusk. A system of mirrors and lenses concentrated the light of the stars, making them visible even under unfavorable viewing conditions. Street lighting appeared in Arab cities for the first time in history. In Baghdad and Córdoba, the main streets were lit by oil lamps mounted on tall poles. The fuel was purified vegetable oil, which burned with virtually no smoke or soot. Special city employees, the predecessors of modern public utilities, monitored the lighting. Arab craftsmen also improved household lamps. They created lamps with adjustable brightness, in which the size of the flame could be changed without extinguishing it completely. Such lamps were equipped with complex mechanisms for fuel supply and airflow regulation to the burner. Arabic camping lamps for caravan trade deserve special attention. These devices had to work in extreme desert conditions, sandstorms, strong winds, and sudden temperature changes. Arab engineers created sealed lamps with an autonomous fuel supply for several days of travel. Arab doctors used concentrated light for medical purposes to treat various diseases. Avicenna described methods of light therapy using a system of mirrors that concentrated sunlight into a narrow beam. This light was used to cauterize wounds and treat skin diseases. Arab achievements in the field of lighting were so significant that they influenced the development of lighting technology throughout the world. The Crusaders brought Arab lamps and fuel purification methods to Europe, marking the beginning of a new stage in the development of European lighting technology. The 19th century was a turning point in the history of lighting. The era of gas lighting marked the transition from ancient technologies to industrial methods of light production. For the first time in human history, artificial lighting became widespread, affordable, and relatively safe. The revolution began in 1792, when Scottish inventor William Murdoch first used lighting gas to illuminate his own home. The gas was produced by heating coal in closed retorts without access to air. This process, called dry distillation, produced combustible gas that could be transported through pipes and burned in special burners. By the 1800s, gas lighting had appeared on the streets of London and Paris. The first gas lamps were simple, open-flame burners, but engineers soon began to improve the design. Burners with calamine screens appeared, special caps made of rare earth metals that glowed in the gas flame and gave off a bright white light. Gas lighting solved many problems that humanity had been struggling with for millennia. It was no longer necessary to constantly refill lamps with oil, trim wicks, or fear accidental fires. Gaslight burned evenly, brightly, and relatively cleanly. Cities were transformed. Nightlife became more active, crime decreased, and the working day extended far beyond daylight hours. However, gaslighting also brought new problems. Gas leaks led to explosions and fires. Combustion products polluted the air indoors. The gas pipeline system required constant maintenance and repair. Engineers began to look for alternative solutions that would retain the advantages of gas lighting but eliminate its disadvantages. An interim solution was to use liquefied gases, propane and butane. These gases could be stored in pressurized cylinders, which made gas lighting mobile. Portable gas lamps appeared for tourists, railroad workers, and sailors. Such lamps provided bright light and worked in all weather conditions. At the same time, gas production and purification technologies were developing. Gas plants were built where coal was processed on a large scale. The gas was purified of harmful impurities, enriched to increase the brightness of combustion, and aromatized to detect leaks. The quality of gas lighting was constantly improving. Theaters and public buildings played a special role in the development of gas lighting. The first remote lighting control systems were created here. Operators could simultaneously light or extinguish hundreds of gas burners. Dimmers appeared, devices for smoothly changing the brightness of light, which formed the basis for modern stage lighting technology. Gas lighting also stimulated the development of optical technologies. Reflectors, lenses, and prisms were used to intensify gas light. Gas searchlights were created for lighthouses, gas headlights for trains and steamboats, and gas lamps with magnifying glasses for precision work. By the middle of the 19th century, gas lighting had reached its peak. Large cities had extensive gas pipeline networks serving thousands of consumers. Gas plants operated around the clock, producing millions of cubic meters of lighting gas. The profession of gas worker became one of the most sought after in cities. However, by the end of the 19th century, the limitations of gas lighting had become apparent. Despite all the improvements, gaslight remained rather dim compared to daylight. Combustion products polluted the air, and the danger of explosions was not completely eliminated. Engineers understood that the future lay in fundamentally new technologies. A transitional solution was to use gas to power electricity generators. Gas engines rotated dynamos that produced electric current for lighting. Such hybrid systems allowed for a smooth transition from gas to electric technologies, using the existing gas infrastructure. The era of gas lighting ended in the early 20th century, but its impact on the development of cities and people's lifestyles cannot be overestimated. Gas lighting prepared society for the era of electricity by creating the infrastructure for centralized power supply and a culture of round-the-clock urban life. In 1881, the first electric lights were lit on the streets of Paris. These were carbon arc lamps, devices that produced a dazzlingly bright light using an electric arc between two carbon rods. The era of electric lighting had begun, forever changing the face of human civilization. The principle of operation of the arc lamp was based on a phenomenon discovered by Russian scientist Vasily Petrov in 1802. When two carbon rods connected to a source of electricity first touch and then slowly move apart, an electric arc is created between them, a stream of ionized gas that emits intense white light. The first arc lamps were capricious devices that required constant attention from the operator. The carbon rods burned unevenly, the arc went out at the slightest shock, and the brightness of the light fluctuated widely. But even imperfect arc lamps provided hundreds of times more light than the best gas burners. The invention of an automatic arc regulator by French engineer Paul Jablotsky was revolutionary. His Jablotsky candle consisted of two parallel carbon rods separated by a layer of special clay. As the coals burned, the clay evaporated, maintaining a constant distance between the electrodes and a stable arc brightness. Arc lamps made it possible to illuminate large open spaces for the first time. A single arc lamp could illuminate an area of several hectares, turning night into day. This opened up new opportunities for night work in factories, mass events, and the development of night trade and entertainment. Arc lamps proved to be particularly effective as searchlights. Military sailors quickly appreciated the capabilities of powerful arc searchlights for illuminating naval battles and detecting enemy ships. Coastal batteries equipped with huge arc searchlights capable of illuminating ships at a distance of tens of kilometers appeared. The theater industry was also revolutionized by arc lamps. For the first time, it became possible to create the effect of bright daylight on stage, imitate sunbeams, and create dramatic lighting effects. Arc searchlights allowed directors to use light as a full-fledged element of stage design. The development of arc lamps stimulated progress in the field of electrical engineering. They required powerful DC generators, sophisticated electricity distribution systems, and precise control and regulation devices. The first power plants were built specifically to power arc lamps. However, arc lamps had serious drawbacks. They consumed enormous amounts of electricity, produced a dazzlingly bright light that was unsuitable for domestic use, and emitted a characteristic hissing and crackling sound. The combustion products of coal polluted the air, and replacing burnt electrodes required special skills. The search for an alternative to arc lamps led to the creation of incandescent lamps. Thomas Edison, Alexander Lodogin, and other inventors experimented with various materials to create a filament, from platinum to carbon fibers. The goal was to find a material that could glow red-hot, emitting light, but without burning up. By the end of the 19th century, arc lamps began to be replaced by more sophisticated light sources, but their role in the history of lighting cannot be overestimated. They were the first to demonstrate the possibilities of electric light, laid the technical groundwork for the development of electrical engineering, and showed society the prospects of a new era of lighting. Many of the principles behind arc lamps are still used today in modern gas discharge light sources. In 1826, British Army officer Thomas Drummond made a discovery that would shape the development of theatrical and military lighting for half a century. He discovered that a piece of lime heated in a flame of hydrogen and oxygen produced a dazzlingly bright white light, visible at great distances. This was the birth of limelight, a technology that became the precursor to modern searchlights. The principle of limelight was based on the property of calcium oxide to heat up to temperatures above 2,000 degrees without melting. Hydrogen and oxygen were mixed in special burners, creating a flame with a temperature of about 3,000 degrees. A small cylinder of pressed lime was placed in this flame, which began to glow with the brightest white light. The brightness of limelight was phenomenal for its time. One lime searchlight provided as much light as 1,000 candles or 100 oil lamps. The light was so bright that it was used for light signals between ships at a distance of up to 50 kilometers. The British Navy quickly adopted lime signal lights. In the theater world, limelight caused a real revolution. For the first time, directors were able to create the effect of bright sunlight on stage, highlight individual actors with directed beams, and create dramatic light contrasts. This is where the expression "to be in the limelight" comes from, which is a literal translation of the English idiom "to be in the limelight," meaning to be in the limelight. Operating lime spotlights required high qualifications and was quite dangerous. Hydrogen and oxygen were stored in separate high-pressure cylinders. The slightest carelessness when mixing gases could lead to an explosion. Lime lamp operators underwent special training and were considered elite specialists in theater technology. To enhance the effect, lime lamps were equipped with lens and mirror systems. Parabolic reflectors collected the light into a narrow directional beam, and the lens system allowed the beam to be focused, or, conversely, scattered. Some theater installations had up to 10 lime spotlights with different optics. Chalk light also found application in scientific purposes. Astronomers used chalk lamps to illuminate the measuring scales of telescopes, which allowed them to conduct observations at dusk. Microscopists used chalk light to study the smallest objects, obtaining illumination that was unattainable with other light sources of the time. Military engineers created mobile lime spotlights to illuminate the battlefield and detect the enemy. During the Crimean War, British troops used lime signal lamps to communicate between positions. The powerful white beam was visible for many kilometers and allowed complex messages to be transmitted using the Morse code. Photographers also appreciated the capabilities of limelight. At a time when photographic plates were insensitive and required long exposures, bright limelight reduced exposure times to a few seconds. This made it possible to take portraits in studio conditions and photograph moving objects. The development of limelight stimulated progress in the field of gas technology. Safer methods of obtaining and storing hydrogen and oxygen were developed. Gas mixing systems were improved, and automatic fuel regulators were created. Many of these inventions were later used in other industries. By the end of the 19th century, limelight began to be replaced by electric arc lamps, which were safer to operate and did not require expensive gases. However, lime lamps continued to be used in some special applications until the mid-20th century. Their operating principles formed the basis for modern gas burners and plasma light sources. At the end of the 19th and beginning of the 20th centuries, inventors around the world experimented with the most unusual ways of producing light. This era gave rise to many forgotten technologies that seemed promising, but could not compete with incandescent lamps and were later consigned to oblivion. One of the most mysterious inventions was Nikola Tesla's induction lamps. The great inventor created a wireless energy transmission system that could light lamps without wires at a distance of several meters. In a glass bulb filled with rarefied gas, a glow similar to the northern lights appeared under the influence of a high-frequency electromagnetic field. Tesla demonstrated his wireless lamps at world exhibitions, astonishing the public. Spectators saw the bulbs light up in the inventor's hands, even though there were no wires connected to them. It seemed as if Tesla had mastered the magic of light. However, the practical application of induction lamps was limited due to their low efficiency and the need to be close to the transmitter. No less exotic were radioluminescent lamps, which used the energy of radioactive decay to produce light. In the early 20th century, when the dangers of radiation were not yet understood, radium was added to special phosphorus compounds that coated the inner surface of the lamps. Radioactive particles excited the phosphorus, causing it to glow with a greenish light. Such lamps did not require an external energy source and could shine for decades. They were used in aviation to illuminate instrument panels, in the watch industry for luminous dials, and in the military for night lighting of maps and equipment. Only after several decades did it become clear how dangerous these devices were to health. Chemists experimented with chemiluminescent light sources, substances that glow as a result of chemical reactions without releasing heat. The most famous example was the reaction of luminol with hydrogen peroxide, which produced a blue glow. The military developed disposable chemical flashlights for signaling and emergency lighting. Biologists tried to use living organisms as light sources. Cultures of luminescent bacteria were grown in special vessels to create biological lamps. In tropical countries, experiments were conducted with large clusters of fireflies kept in special terrariums. These living lamps gave off a soft, pleasant light, but were extremely impractical. Engineers invented mechanical light sources based on friction. Friction lamps worked on the principle of flint and steel on a larger scale. Rapidly rotating metal discs struck sparks from special materials. Some designs could maintain a continuous stream of sparks, creating a kind of glowing torch. Of particular interest were solar concentrators, devices that collected sunlight from a large area and directed it to a single point. French inventor Augustin Mouchot created a solar furnace several meters in diameter, capable of melting metals with the power of concentrated sunlight. Such installations provided extremely bright lighting during the day, but were useless in cloudy weather and at night. Pneumatic lamps used the energy of compressed air to create light. A jet of high-pressure air was passed through a special burner, where it was mixed with combustible gas, creating a brightly burning flame. Such lamps were popular in mines and other places where the use of electricity was dangerous. Acoustic light sources were based on the conversion of sound vibrations into light. Powerful sound waves excited special crystals, causing them to emit light. Although the efficiency of such devices was extremely low, they demonstrated a surprising connection between different forms of energy. Most of these exotic technologies did not become widespread due to their complexity, high cost, or low efficiency. However, many of the principles behind these forgotten inventions have found application in modern technologies, from LEDs to lasers. In the 21st century, interest in ancient lighting technologies is experiencing a real renaissance. Armed with advanced research methods, modern scientists are rediscovering the secrets of our ancestors and finding that many ancient solutions were far more sophisticated than previously thought. Archaeological optics has become a new field of science, combining archaeology, physics, and engineering. Researchers use laser scanning, computer modeling, and spectral analysis to study ancient lighting systems. Three-dimensional models of temples and palaces allow them to accurately recreate the paths of light and understand the principles of forgotten technologies. Professor Mark Lenner of the University of Chicago conducted revolutionary research on the Pyramid of Cheops using modern computer modeling techniques. He discovered that the inner chambers of the pyramid were part of a complex optical system that directed sunlight from the entrance to the pharaoh's burial chamber. Calculations showed that on certain days of the year, a ray of sunlight illuminated the pharaoh's sarcophagus, symbolizing his resurrection. An international team of researchers led by Dr. Julia Sprague of Oxford University is studying Byzantine churches using photogrammetry and laser scanning. Scientists are creating accurate 3D models of Hagia Sophia and other cathedrals, allowing them to track the movement of light throughout the day and understand how architects used natural lighting to create a mystical atmosphere. Of particular interest is the research of Dr. José Antonio Belmonte from the Canary Islands Institute of Astrophysics. He studies the astronomical aspects of ancient lighting systems, discovering connections between temple architecture and the movement of celestial bodies. It turns out that many ancient lighting solutions were linked to astronomical calendars and religious holidays. Modern chemists are re-examining ancient recipes for oil lamp fuel. Dr. Andreas Schmidt from the Technical University of Munich recreated the composition of Egyptian lamp oil using chromatography mass spectrometry to analyze residues from archaeological finds. He discovered that the Egyptians added extracts from certain plants to the oil, which improved combustion and reduced smoke. Physicists at the Massachusetts Institute of Technology are studying the optical properties of ancient mirrors and lenses. Professor Sarah Mitchell discovered that some ancient Roman mirrors had a slightly curved surface rather than a flat one, which allowed them to focus reflected light. This discovery has led to a rethinking of the ancient world's knowledge of optics. Researchers at the University of Tokyo are using computer vision techniques to analyze the distribution of soot in ancient temples. Using special algorithms, they can determine the exact location of light sources thousands of years ago and reconstruct the ventilation systems that kept the walls clean when open fires were used. Interdisciplinary research brings together archaeologists, engineers, chemists, and physicists. The European project LIGHT-ARC, Light Technologies in Ancient Architecture, coordinates the efforts of scientists from 15 countries to create a complete picture of the development of ancient lighting technologies. Researchers exchange data, methodologies, and discoveries, creating a common knowledge base about forgotten technologies. Modern methods have made it possible to discover lighting systems where they had not been noticed before. In the Angkor Wat Temple in Cambodia, the remains of a complex system of water mirrors were found that reflected sunlight into the temple. Stone lenses were discovered at Machu Picchu that focused the sun's rays for religious ceremonies. The results of modern research are radically changing our understanding of the technological capabilities of ancient civilizations. It is becoming clear that our ancestors possessed knowledge in the field of optics that was considered lost until the Renaissance. Many principles of ancient lighting technology are surprisingly modern and can be applied to today's energy-saving and environmentally friendly lighting technologies. Scientists are moving from theoretical research to practical experiments to recreate ancient lighting technologies. Experimental installations are being built around the world, where modern engineers are trying to replicate the achievements of our ancestors, using only the materials and tools that were available thousands of years ago. A full-scale replica of the lighting system of the Dendera Temple was built in the Egyptian Museum in Cairo. An international team of engineers and archaeologists recreated the system of bronze mirrors and solar reflectors using ancient metalworking techniques. The experiment showed that such a system could indeed illuminate the interior of the temple with bright natural light without the use of torches. A group of researchers from the University of Cambridge built a working model of a Roman multi-stage lighting system. Using rock crystal polished by hand, using ancient methods and bronze mirrors made using Roman techniques, they created a device capable of increasing the brightness of an oil lamp 50-fold. The experiment confirmed the descriptions of ancient authors about sunlight at night. The Byzantine Research Center in Istanbul recreated the famous light wells. The builders used only tools and materials available in the 6th century AD. The result exceeded expectations. The system could indeed deliver sunlight to a depth of more than 30 meters, illuminating underground rooms as if they had windows. Experiments with ancient oil lamps were particularly impressive. A team of chemists from the University of Athens recreated the exact composition of ancient Greek lamp oil based on an analysis of archaeological finds. Lamps with this oil burned 3 times brighter than modern oil lamps and produced virtually no smoke. Researchers from the University of Bologna built a replica of an Arab lighthouse with a system of parabolic mirrors. Using polished steel made using medieval technologies, they created a reflector with a diameter of 3 meters. The light beam from such a system was visible at a distance of more than 40 kilometers, confirming the reports of medieval chroniclers about stars on Earth. Japanese scientists recreated an ancient system of bioluminescent lighting using fireflies and special traps. They discovered that, when properly organized, a colony of fireflies can provide enough light to read a book throughout the night. Such a lighting system was completely renewable and environmentally friendly. Experiments with Tesla's induction lamps are being conducted in Serbia, the homeland of the great inventor. Engineers at the Belgrade Technical Institute built a replica of Tesla's laboratory and reproduced his experiments on wireless energy transfer. Modern calculations have shown that under certain conditions, Tesla's system could be more efficient than previously thought. Archaeological experiments are being conducted not only in laboratories, but also in real-world conditions. In the Peruvian Andes, researchers are testing recreated Inca solar concentrators. In high-altitude conditions, such systems show remarkable efficiency, concentrating sparse sunlight into powerful rays. Computer modeling helps optimize ancient designs. Using modern lighting calculation programs, engineers can predict the behavior of lighting systems in various conditions and make adjustments to ancient designs. Some recreated systems work even better than the originals thanks to precise parameter tuning. The results of experiments are often unexpected. Many technologies that were considered primitive demonstrate surprising efficiency. Ancient lighting systems often surpass modern counterparts in energy efficiency, durability, and environmental friendliness. This forces us to reconsider our attitude toward technological progress and think about the fact that not all old technologies should be forgotten. Practical experiments become a bridge between the past and the future. By recreating ancient technologies, scientists not only satisfy their scientific curiosity, but also seek solutions to modern energy and lighting problems. The study of forgotten lighting technologies opens up amazing opportunities for the modern world. In an era when humanity is looking for environmentally friendly and energy-efficient solutions, the experience of our ancestors can be a source of inspiration for creating the lighting technologies of the future. The principles of passive solar lighting developed by ancient architects are finding new applications in modern construction. Japanese architects are creating office buildings with light wells based on Byzantine technologies. A system of mirrors and light pipes delivers natural light to the deepest parts of buildings, reducing electricity consumption by 70%. Modern LEDs are combined with ancient optical systems to create ultra-efficient lighting fixtures. A German company has developed street lamps, in which the power of LEDs is amplified by a system of parabolic reflectors based on Roman technology. These lamps consume 5 times less energy while providing the same brightness. Bioluminescent technologies are experiencing a renaissance in the era of biotechnology. Genetically modified bacteria and algae create living light for decorative lighting in parks and public spaces. French urbanists are experimenting with living lanterns, trees with glowing leaves that provide soft, environmentally friendly street lighting. Ancient principles of concentrating sunlight are being applied in modern solar technologies. Solar power plants use mirror systems reminiscent of Arabian light towers to concentrate solar energy. Such installations can generate electricity even in cloudy weather by using scattered sunlight. There is a resurgence of interest in mechanical light sources. Swiss engineers have created bicycle dynamo machines based on the principles of medieval mechanical lamps. The energy from pedaling is stored in batteries and used for lighting in remote areas not connected to electrical grids. Chemical light sources are used in emergency situations. Modern chemical flashlights, based on ancient principles of chemiluminescence, do not require batteries and can operate in extreme conditions. Rescue services use such devices when dealing with the aftermath of natural disasters. Ancient methods of obtaining clean fuel inspire modern chemists to create environmentally friendly energy sources. The processes for purifying vegetable oils developed by Arab alchemists are being adapted for the production of biofuel from food industry waste. Such fuel burns cleanly and does not pollute the environment. The optical principles of ancient lighting systems are used in modern fiber optic technologies. Engineers are creating long-distance light transmission systems based on ancient principles of sequential reflection. Such systems allow underground structures to be illuminated with natural light without consuming electricity. Smart materials embody ancient dreams of self-illuminating surfaces. Photoluminescent coatings accumulate solar energy during the day and release it in the form of a soft glow at night. Such materials are used for road markings, stair lighting, and creating safe pedestrian areas. The Internet of Things combines ancient lighting technologies with modern electronics. Light sensors automatically control mirror and reflector systems, optimizing the use of natural light throughout the day. Artificial intelligence analyzes weather conditions and astronomical data to predict optimal lighting modes. Urban planning takes into account the experience of ancient architects in creating light landscapes. New areas are designed with the movement of the sun and the location of reflective surfaces in mind to maximize the use of natural light. This approach allows for the creation of a comfortable lighting environment with minimal energy consumption. Educational programs include the study of ancient lighting technologies as part of humanity's engineering heritage. Students at technical universities study the principles of Roman lighting systems alongside modern photonics, understanding that innovation often comes from rethinking old ideas. Forgotten lighting technologies remind us that the path to the future sometimes lies through the past. In our quest for sustainability and harmony with nature, We can learn a lot from our ancestors, who created light from the sun, water, and fire without depleting the planet's resources or polluting the environment.